So moving on to our next section in Unit 5, we're going to take a look at a topic that might seem very familiar to you if you've taken a physics course. And we're going to deal with what's called particle motion in this section, the next section, and actually a little bit later on this year. Now we have to make sure that we are kind of particular or familiar with two things in relation to this particle motion. Obviously, objects can move in every direction, such as a fly or a human or whatever the case may be. But to simplify things, this Calc 1 course only deals with particles moving along the x or y axis. So that means we're only going to be dealing with particles that are moving left or right or up and down. So they're not going in a diagonal path or a circular path. They're strictly moving left or right or up and down. When you get into Calc 2, we start to talk about curved paths or diagonal paths, but for right now we're just going to focus on left, right, and up and down. When we talk about particle motion, there are different properties that we can analyze about that particular particle. One of those properties is called position, so that's basically where is the particle located. We can also talk about velocity, meaning how fast is the particle traveling, but also in what direction. So is it moving left or right or down or up? And we can also talk about its acceleration. How fast is its speed changing in that case? Now, since we're only moving left or right or up or down, those are our only four options. When we start to look at graphs that represent position, sometimes those graphs could be parabola shapes. For instance, if you throw a ball up in the air, the initial position might be 0, or the basic height off the ground, and as you throw the ball up into the air, notice how the position increases. Okay, it's getting higher and higher. It eventually reaches its max height at the very top, and then gravity pulls the ball back down to the surface. So the position would be decreasing. So even though the ball is only moving strictly up and down, notice how its position graph might look something like this over time. So the x-axis might represent some time unit, like minutes or seconds or hours, whatever the case may be. So we have to be sure that we understand that whenever we have a position graph, the particle is not traveling along the path of this graph. Okay, this graph is only describing the location of the particle. Okay, so position is defined by functions. The particle does not move along the graph of that function. Okay, we have to be kind of clear about those two things. So what we're going to do today in this video assignment is just formally define velocity and acceleration. I'm already assuming that we know position just means location, but these two new words might be a little bit different for us or new to us in terms of calculus or terminology. So when we talk about average and instantaneous velocity, we've already seen these two words before, average and instantaneous, and typically up to this point, following those words have been rate of change. Now, in this case, we're dealing with velocity. So velocity is technically representing the rate of change of something, but we have to kind of think about what that something is. So we'll write down rate of change of something. Okay. Now, velocity we can kind of think about as speed with direction. So if we have a negative velocity, that means we're either moving left or down, and if we have a positive velocity, we're either moving right or up. The numbered value is just representing the speed, okay, how fast we're traveling. And if you think about the concept of speed, for instance, miles per hour, that's how fast your location, aka your position, is changing. Are you moving very quickly? Are you moving very slowly? So velocity is technically referred to as the rate of change of position. Now, since we have two different types of rate of change, average and instantaneous, we have different ways now to calculate these values if we know a position function or perhaps graph. So we'll say, maybe I'll abbreviate instead of writing all this out. I'm going to say average velocity is technically the slope between 2 points. Okay, that was our previous definition of average rate of change. So if we have average velocity, that's the slope between 2 points on the position function or the position graph, whatever information might be provided to us, or table even, because that's another piece. If we do instantaneous velocity, that's the slope at 1 point on the position function or table or graph. And if we're dealing with a slope of 1 point, we can use a synonym that we're very familiar with called derivative. So instantaneous velocity is technically the derivative of position. So keeping those two types of rates of change in mind, let's take a look at an example to kind of bring this together. So a particle's position or location is given by this function, where P of t is measured in centimeters and time is measured in seconds. Answer the following questions. So they don't really specify the direction in which this position is traveling. We don't really know if it's moving left or right or up or down, but at least we know something about its location. All right, so what is the average velocity on this interval? And then make sure you use some units because we have those provided to us. So average velocity is the slope between 2 points on the position, in this case, equation. And since they're giving us those interval points, we can use those to our advantage. So slope between 2 points, we're going to need x values and y values. We already have the x or t values given to us, so let's go ahead and plug in 1 and 3 to get our y values. So e to the first times sine of 1. We get 2.2874. All right, and I'm going to do the same thing, but plug in 3. 2.8345. I guess technically we should go out one more decimal because this is not our final answer. We should only be rounding our final answer to 4 decimal places. So I'll do 28736. And then this one I'll do 83447. All right, so we need the slope between those 2 points. So we'll say average velocity is equal to the change in the y's over the change in the x's. All right, so quick calculation here. And I got 0.2729 if we round it. All right, so notice how our velocity is positive. Our average rate of change is positive. So we know our position is increasing. Okay, the rate is positive, so our position function is going up. Our position is increasing. If we think about the units, we need a y unit over an x unit. So we got to think about what did these two numbers represent in terms of units, and then what did these two numbers represent in terms of units. So these numbers were the y values from position, and position was measured in centimeters. And then these two numbers were our time units, which were seconds. So our average speed, if you will, is this value, centimeters per second. All right, let's go ahead and try the next one. What is the instantaneous velocity? So this would be the slope at 1 point, aka the derivative of position. So we already know our position function is given to us. Let's find the derivative of this. So e to the t times sine of t, we'd have to use our product rule because we're multiplying two things together. We'll have 1 d2 plus 2 d1. The derivative of e to the power is e to the power. Technically, we should multiply by the derivative of the power, but the derivative of t would just be 1. So this is actually our instantaneous velocity function, okay, the derivative, the rate of change at 1 point. So I'm going to go ahead and plug in 1.5 into all those t's, and then we'll see what we get. So e to the 1.5 cosine 1.5 plus sine 1.5 e to the 1.5. 4.7875. Now you could also truncate or just chop it off at 4, but you can round whatever your preference is. All right, now since this is, again, rate of change and it's of velocity, it's still going to have the same units. This is just representing the rate of change at one point in time. So at this point in time, this is how fast the particle is traveling. This is how the rate at which its speed is changing. Okay, in this case, increasing because it's positive.